I wanted to start class today where you consider the maximum of two random variables. And let's think about an application. So you've got three people, and I'm not going to say their names. I'll just say these three people have names that start with X, Y, and W. Why not X, Y, and Z? Well, I want to reserve Z for standard normal random variable. And they are three roommates. They each have separate rooms and separate bathrooms. They each get up at the same time every morning. Maybe there's one alarm that goes off for everybody. They each get up at, let's say, should we get up as early as I do? 5:30 a.m. Anybody? Really? I get up that early? Yeah, I do. In fact, I even just wake up. I don't even need an alarm. I wake up at 5:30 every morning. Okay, no, let's say 6 a.m. They each get up at 6 a.m. and they go together to school or to work or whatever. But W takes a shower the previous night, and so W is always ready pretty quickly, just has a quick breakfast, is ready to go. X and Y, they take showers in the morning, so they're slower, okay? So let's say X and Y's time, but let's phrase it like this, time to be ready to leave that they have the same distribution is exponentially distributed. Exponentially distributed, I should have said. With what mean? Oh, maybe half an hour. Well, okay. Let me not specify the exact mean. Remember, with exponential distributions, our book called the mean beta initially. Yes, this is the mean mu. We could say beta equals mu. We can also relate this to lambda, which was the Poisson distribution parameter. Lambda equals 1 over beta. We're actually going to use the lambda more than the beta in what I'm about to show you here. So X and Y, they take showers, they take longer, but the time that they're ready to leave is exponentially distributed with mean beta and the lambda corresponding to a Poisson distribution equal to 1 over beta. So what does this mean? That means their PDFs, F sub capital X of little x and F sub capital Y of little y, do have the same formulas, 1 over beta e to the negative x over beta for x, and 1 over beta e to the negative y over beta for y. These are the same functions. I'm using different variables to say I've got two different people effectively. In terms of lambda, this would be lambda e to the negative lambda x and lambda e to the negative lambda y. And W, again, who gets done really quickly, well, W always waits for X and Y. So W is always ready to go whenever both X and Y are ready to go. Now, X and Y have the same distribution, but that doesn't mean on any individual morning that they're going to take the same amount of time to get ready. But W always waits for both of them. So the wait time for W is the maximum of X and Y. W is the wait time to be ready to leave for person W, and that's going to be the maximum of X and Y. The question is, what is the distribution of W? In particular, what is the PDF of W? All right, you did this on your exam with the lambda effectively equal to 1. It was the last problem. How many people got it right? Not many, actually, like 5 people got it right. Okay. How do you do this? Use the CDF method. I gave you some guidance on this. CDF method is to find the CDF for W first, and then differentiate it to find the PDF. So the guidance I gave you is to remind you that the CDF of any random variable is always the probability that that random variable, in this case, capital W, is less than or equal to the given number, little w, say. But what is capital W? It's the maximum of X and Y. So that's just a replacement right there. Then you have to ask yourself a question. What does it mean for the bigger maximum of two numbers to be less than some other number? It means they both have to be less than that other number. To say the maximum of X and Y is less than little w is to say that X is less than or equal to little w and Y is less than or equal to little w. So this was how far of guidance I gave you on the exam to get you this far. How do you go from here? Well, there's something I haven't said yet that I need. I need to assume not only are X and Y exponentially distributed, I need to assume they are independent. Assume X and Y are independent. And if these two roommates, they do have different rooms and different bathrooms, and there's no problem with hot water, like if one's taking too much hot water, the other gets cold water and that kind of thing. It makes sense to assume X and Y are not communicating, they're independent of each other. It is an assumption, though, for the sake of finishing the problem, finishing the model for W. Now I use independence. How? It's the multiplication rule for independent events. This is going to be the product of the probability that X is less than or equal to W times the probability that Y is less than or equal to W. That's independence right there. I don't know if you remember back when we talked about that multiplication rule for independent events, I said this might be the most important equation in mathematical modeling. Here's one example of its use. Everywhere in statistics, assumptions of independence help derive formulas. Can we really prove independence in this situation? Probably not. It's a modeling kind of thing. But if it seems reasonable, then we go ahead and make the assumption and hope the model's good enough, but then we compare it against reality. If you're in operations research, are you talking about modeling and you know, you'd make assumptions and you hope it's good, but you got to compare it against reality. You got to test the model. We're not doing any testing here. We're just assuming and hoping it works. But how do you do this? Well, this is the CDF of capital X. Plug in little w. This is the CDF of capital Y. Plug in little w. Don't plug in little x and little y. There are no little x's or little y's in here. Just little w's. Is that a big deal? Yeah, you should be consistent. One common mistake was sometimes people put an X and a Y in there. Well, do I have those CDFs? I did not write them down. I wrote down the PDFs. What are the corresponding CDFs? Capital F sub capital X of little x. It's an antiderivative of this, whose graph, since the random variable is non-negative, goes to the origin. A little bit of experimentation reveals that 1 minus e to the negative lambda x works. That is a function whose derivative is what I'm pointing at there with my left hand. And capital F of 0 is 1 minus e to the 0. 1 minus 1 is 0. You can also check it's got a limiting value of 1 as x goes to infinity. And capital F sub capital Y of little y is the same formula, except use a little y. Effectively, it's the same function because it's the same distribution, just different letters. Down here, you got to use a w, though. This is going to be 1 minus e to the negative lambda w times itself. I'm squaring that thing. FOIL it out, you'll get 1 minus 2 e to the negative lambda w plus e to the negative 2 lambda w. When I multiply these two things, the last times the last, right? I'll add those exponents and get negative 2 lambda w. This is a lambda here. So lambda not an x. That's the CDF. Now differentiate it to find the PDF for W. Oh, what's it going to be? What's it going to be? Is it going to have an exponential distribution? It's got exponential functions in it. What's the derivative of this? 0 is the derivative of 1. Differentiate this, get an extra factor of negative lambda plus 2 lambda e to the negative lambda W. Differentiate this, get an extra factor of minus 2 lambda e to the negative 2 lambda W for W positive. That is more complicated than the PDF of an exponential. Evidently, it's not an exponential distribution. What does the graph look like? We'll still be using technology quite a bit. What does the graph of this look like? Let me enter it in Mathematica with lambda as a parameter. I'll make it a subscript. Remember to use a capital E in Mathematica for the number E. There's the PDF. What does the graph look like? Well, let's put it inside and manipulate so that we can change lambda. That'll allow us to change lambda with a slider to see how the graph changes. Plot f sub lambda of W going from 0 to 5, say. W is the maximum of X and Y. It is a wait time. If X and Y average, say, a half an hour, if their means are 1/2 so that their lambdas are 2, the beta would be 1/2, the lambda would be 2. Maybe closer to smaller numbers would be good to graph. Fix a plot range in the vertical direction, say 0 to 1 initially. And let lambda vary. I'll start lambda out at the value that I hinted at, that maybe they take person X and person Y take values of 1/2 on average. But we could go lower down to say 1/10 and up as high as 10 and just see how it affects the graph. So this syntax is going to give us a graph with a slider starting at lambda equals 1/2. I'll be able to move the slider down to 1/10 or as high as 10. See how it affects the graph. So this is the case where lambda is 1/2. Actually, I should start lambda at 2 instead of 1/2. 1 over lambda is the mean. So if lambda is 2, the mean is 1/2 an hour, say. So the mean of this graph is 1/2 an hour when lambda is 2. That's the center of mass of this graph, which is a little surprising to me. Actually, I would have guessed it would be a little higher here based on what I see. If I lower lambda, make it smaller, that increases the mean, so the graph is going to shift to the right, so to speak. The mean gets bigger. If I increase lambda, then the mean gets smaller. Does it really integrate to 1? Is it always a PDF? Let's try it. Mathematica, integrate this from 0 to infinity. F sub lambda of W dW. Thinking. Come on. Yeah, wait, 1. If, what's that? RE lambda is greater than 0. Okay, Mathematica is a bit too fancy for its own good sometimes. Mathematica is assuming lambda could be a complex number. And RE of lambda being positive means what's called the real part of lambda is positive. If lambda is a real number, that means lambda itself is positive. Is there any way to avoid that extra condition here? If we integrate with the built-in function integrate, like this, which is an alternative way of doing it, and this allows us to add an extra comma and the word assumptions, arrow lambda is positive, and then it says the answer is 1 right away without bothering to put that extra condition in there. That's telling Mathematica, assume lambda is positive. That's the way that syntax goes, but it seems to only work if you put it inside integrate as a written command instead of a symbol. So it does seem to be a PDF. What's its mean? I guess I need to integrate W times the PDF, right? Mean, expected value, 3/2 lambda. Not double lambda, not 2 over lambda, not double 1/lambda is what I meant to say. Beta is the mean for X and Y. Lambda is 1/beta. That's equivalent to saying beta is 1/lambda. 1/lambda is the mean. The mean for X and Y, the mean for W is not twice that. It's not 2/lambda. It's 1.5 times that. 3/2 lambda. So on average, person W doesn't have to wait twice as long as the average of X and Y. The average wait time for W is not 2 hours, it's not 1 hour, which is double half an hour. It's 45 minutes, which is 1.5 times half an hour. Is there a way to confirm this is right? Well, let's also compute the variance and standard deviation. Integrate W squared times the PDF to get the second moment. Take that and subtract the square of the first moment. The percent sign refers to the preceding output. That'll be the variance, 5/4 lambda squared. Take the square root of that to get the standard deviation. Really, square root of 5/2 times 1/lambda is what this would simplify to when lambda is positive. That would be the standard deviation. Is there a way to confirm this is right? Do we really believe the theory? This is something you might have to do on the job. You know, you're thinking about trying to model some situation. Maybe you can do some theory like this, and maybe you get an answer like I got, but you're wondering, is it really right? Doing simulation would be a way to check to see if it seems right or not. How would we do the simulation? Let's pick a value of lambda like 2. Let's do this thing that we did last week. Or was it the week before? Probability distribution. I think we did this a week ago. What's the syntax? I better look it up just to make sure I'm doing it right. Probability distribution. The syntax is to have my PDF here and then the interval that I'm thinking about right there. Zero to infinity in this case. When you enter this, seemingly nothing happens. But, well, let's pick a value for lambda, like 2. But the mean, the variance, the standard deviation, all those can be found. The mean, what should the mean be if this is right? It should be, if lambda is 2, it should be 3/4. Yeah. What about the variance? If lambda is 2, 2 squared is 4, 5/16. Standard deviation would be the square root of that. Approximately 0.56. Now use RandomVariate to do a simulation to really be even more sure. Syntax is if I've stored the output of this thing in D, whatever that means, I can put D here, and if I do a comma, say 100, I get a random sample of size 100 from this distribution. Let's do a size 1,000 and suppress output. What's the mean of that? Hopefully it's close to 3/4, 0.75. Will it be exactly 0.75? Probably not, but should be close. Yeah, pretty close. Standard deviation. Is this doing the divide by n-1 standard deviation? I think so. Close to 0.56. These are close together. I could make plots like you find in chapter 6. Number line plot makes a dot plot. There's all the data. Reflecting the density the data are denser where the density itself, the PDF, is higher. I could also make a histogram. Not a relative frequency histogram, but a total count histogram. The vertical axis represents a total count. So for example, this interval has 200 numbers in it. What interval is that? If that's 0.5 there, this would be 0.2 and 0.4. There's evidently 200 data values that are between 0.2 and 0.4. What's the relative frequency of that? You can convert that to a percentage. There was 1,000 data points, 200 divided by 1,000 is 20%, 0.2. You can relabel the axes to be the relative frequencies, as you should have read about in chapter 6. You can make a box and whisker plot too. Box whisker chart data. Showing the 5-number summary. What's that? That's the minimum. Well, you can see the 5-number summary here. Kind of small numbers. That smallest number at the very bottom that only people in the front row can see is about 0.013. That's the minimum. The first quartile, same as the 25th percentile, is the spot at which 25% of the data are less than it. It's about 0.36 if you can't quite see it. 0.36 is a data value at which about 25% of the data are less than it. It's in the 250th spot if you put the numbers in order from least to greatest. The median is the 50th percentile. It's about 0.63. The third quartile is about 1, real close to 1. Same as the 75th percentile. And the maximum is up here at 3.5. Can I find the 3.5? Oh, I don't know if I want to look through 1,000 numbers. It's somewhere in there. I'm not going to look for it. Is 3.5. I don't know how much reading you actually did about making graphs in chapter 6. I hope you read it. It's kind of technical. If I have you make a box and a whisker plot like this, technology is fine. Don't worry about the technicalities of finding quartiles, for example, or finding what are called inner and outer fences, as you'll read about if you haven't read about it. Don't worry about those technicalities. If you make a graph like this showing the min, the first quartile, the median, the third quartile, and the max found from technology, it's fine as a box plot or box and whisker plot. But the fact that the maximum is so much further from the median than the minimum is, same with the third quartile being farther from the median than the first quartile is, it's telling us this is a right skewed distribution. And in fact, if you're going to make one of these plots by hand, I'd suggest drawing it on its side instead of up and down. Just fits better on paper. And if you fit it on paper with larger numbers going to the right, as they usually do, it's a long right tail. Would be a right skewed distribution, which is what you see with the histogram as well. And the PDF as well. It's right skewed. There are once in a while very high outliers that affect the mean to pull it to the right more than the median, say. Here's one more interesting thing we can do. I can also, well, let's do it two separate times. I could also do data on X and Y itself with RandomVariate, and then I could find their maximum and see if it seems to follow this distribution as well. This would be one more way to check it. I don't need to use probability distribution. I can use built-in exponential distribution. Let's go ahead and assume lambda's 2. Mathematica doesn't use beta as the parameter in this function. It uses lambda. So lambda equals 2 is going to give me data with a mean close to 1/2. 1,000 data points. I'll do the same kind of syntax for y values. Just change data x to data y. Both the mean of data x and the mean of data y should be close to 1/2, representing an average of 1/2 an hour. Yep, both close to 1/2. And then if I do data w, what's the best way to do this? I'm not going to explain this, but if I use table and max in the following way, I can compare each value in data x with the corresponding value in data y. I goes from 1 to 1,000 to get 1,000 observed values at the maximum of x and y. So effectively, this is like representing 1,000 days worth of getting up at the same time every morning, and x and y taking a shower, and w not, but w waiting for x and y. And the total time before they all leave is the maximum of x and y. The mean of data w hopefully is close to 0.75. Yeah, not too far away. Well, that's a lot to think about. I've shown you a lot here in a short amount of time. But this is really, really useful way to think about things, both theoretically and with simulation, to confirm your theory does seem to be on track. But once again, we are really emphasizing in the theory the power of the CDF method. It really is a powerful method. You might also wonder, could I do something similar with the minimum of x and y instead of the maximum? The answer is yes, you can, but it is a little tricky. A little trickier. The min of x and y being less than or equal to a number w, meaning the smaller of x and y being less than or equal to a number w, means either x is less than w or y is less than w, or both. You would have the word or in there instead of and. How do you deal with that? You can use the general addition rule. That would be the probability of this plus the probability of that minus the probability of this and that. So it'd be more complicated, but could still be done. You would get a different answer. That might be something interesting that you'd like to try. I want to continue with this example now and relate it to what we've learned about in chapter 7. What we found in this example is that the expected value of w, which is the expected value of the maximum of x and y, where x and y have exponential distributions with parameter lambda, and they're independent. We saw with technology is 3/2 lambda. 3/2 times 1/λ, where 1/λ is the mean of x and y. You could also call it beta. You might wonder, if I've got data about w, is there a way to estimate lambda? The key thing to do is to take this equaling this and rethink about it in terms of estimators. How would you do that? What does that mean? The expected value of w is a number. If lambda is fixed, it's a fixed number. It's a parameter. It's a population parameter. Its natural estimator, we'd probably call w bar, right? Sample mean. This is where you got to get your concepts clear. Expected value of w is a number, a parameter that describes the population distribution of w. W bar is its sample mean. We've got a bunch of observed values of w. We take their arithmetic average. We add them up and divide by how many there are. Divide by n, say, for a sample of size n. Natural, and in fact, we saw last time, unbiased estimate for this. The mean of the mean is the mean. Remember that? I could call this mu sub W. I could write the expected value of W bar equals mu sub W. Very important fact here. The mean of the mean is the mean. Again, W bar is a logical and unbiased estimator for mu sub W. What's an estimator for lambda? Well, I don't know it yet. But what would be a logical estimator? Maybe I can solve for it. Maybe I can take the fact that this number equals this number and say that this statistic should equal this statistic. What did I do there? I put a little hat above the lambda. This should not be completely mysterious if you read chapter 7. Putting a little hat above the lambda is a statistician's way of indicating that this thing is supposed to represent what's called an estimator for the parameter lambda. And remember, get these concepts right. An estimator is a statistic. What does that mean? It means it's a function of a random sample. W bar in particular is this function of the random sample, capital W1 plus capital W2 plus etc. through capital Wn divided by n. That's what that function of a random sample is. That's what a statistic is. It's a function of a random sample. It itself is a random variable. It itself has a distribution and an expected value. Lambda hat is evidently also a statistic, because we could solve this equation for lambda hat in terms of W bar. How? Just do the algebra. Multiply both sides by lambda hat and divide both sides by W bar. Lambda hat would be 3/2 times W bar. This would also be a statistic then, because you can compute this from a random sample. I could even write its formula in terms of the random sample. I could replace W bar with W1 plus W2 plus ... plus Wn over n. And then I could even simplify this a little bit by multiplying the top and the bottom by n and get 3n/2 times the sum of the w's. I could do that. There's no problem with that. It's not something people typically do, but it could be done. This is a statistic, though. It's a function of the random sample, defining a new random variable that would have a distribution, a PDF, a CDF, a mean, a variance. And it is, in this context, a natural estimator for lambda, based on this method of taking this expected value and replacing it with a natural estimator. First moment, mean, W bar, and taking this parameter lambda and replacing it with its unknown estimator, call it lambda hat, and solving for lambda hat in terms of W bar. I come up with a natural, you might say, estimator for for lambda. In fact, this method that I just used has a name. It's called the method of moments. This method that I used here is called the method of moments, or how about MOM for short? Thanks, Mom. I've come up with the method of moments estimator for lambda. Here I called it a natural estimator. Technically, it's the method of moments estimator, the MOM estimator for lambda. Is it the only possible estimator for lambda? Not necessarily. There could be other estimators for lambda. In fact, you can do strange things. If you wanted to, you could take 3 over 2 W bar and then add 1 over n to it for some strange reason, or 1 over n squared. If n is large, 1 over n or 1 over n squared are small, and so adding such a number to this would not alter it that much when n is large. So you could argue those more complicated and weird kinds of things are also estimators for lambda. But this is certainly simpler, more natural, and probably better. How would you apply this? Well, let's go back to our data. I did this to get data for W here. 1,000 numbers formed by this process of taking the maximum of data from X and data from Y for each day effectively. And I got a mean. I got 0.77994. I could use this estimator, this formula, to get the corresponding estimate for lambda. Compute 3 over 2 times the mean. If I do 3 over 2 times 0.779944, this should be a method of moments estimate for lambda. What should it be close to? It should be close to 2. These data were generated using lambda equals 2 for the distributions of X and Y. And so therefore, we should expect to get a number close to 2. Get the terminology right. Lambda hat equals 3 over 2 W bar is an estimator for lambda. It's a statistic. It's not a number. But if I observe a value for W bar and get a number here and plug that number in like I just did a minute ago, then I get an estimate for lambda. Distinction between the words estimator and estimate. You might wonder, is lambda hat an unbiased estimator for lambda? Unbiased estimator for lambda. Question, i.e., is the expected value of lambda hat equal to lambda? The answer is we don't have any properties that would tell us the answer. Maybe it is, maybe it's not. My guess is it's not. What's the formula for lambda hat? It's 3 over 2 times W bar. And we do know W bar is an unbiased estimator for mu, which is 1 over lambda. But that does not mean I can just replace this W bar with a 1 over lambda, because there's no property about expected values that would allow us to do that. I could bring the 3 halves out in front, but the expected value of 1 over a random variable is not 1 over the expected value of that variable. I cannot, in general, do this. I cannot say the answer is 3 over 2 beta. Let's put it that way. It's not equal to in general. You might wish that were the case, but in general, it's not.